In this video, we want to learn how we can use L'Hopital rule for finding limit of a given sequence. Look at this sequence here. an is given ln of n over n. Because this sequence is in the form of fraction and we can find derivative of ln, which is in the numerator, and derivative of n, which is in denominator, so we can think to using L'Hopital rule for finding limit of this sequence. So instead of finding limit of n approaches infinity of ln of n over n, we change n to x, we change variable n to variable x, and we are finding limit of ln of x over x as x approaches infinity. Because attention that when you write n is an integer number, and you cannot take derivative of an expression when the variable is only integer. You have to change the name of the variable from n to x, then x belongs to real numbers. Then it makes sense to use L'Hopital rule. Of course, you can use L'Hopital rule for this and find the limit. But mathematically, your solution is not right. If you want to make your solution 100% right, always change the variable from n to x, then use L'Hopital rule. Okay, here we have to find limit of ln of x over x as x approaches infinity. And we want to use L'Hopital rule. And we can use L'Hopital rule because we have a fraction, and this is infinity over infinity limit. Because attention, when x approaches infinity, ln of infinity is infinity, and in the denominator also we have x which approaches infinity. And if you remember, when we have 0 over 0 or infinity over infinity, in these two cases we can use L'Hopital rule. So we can use L'Hopital rule for finding this limit. Based on L'Hopital rule or L'Hopital method for finding limits, we have to take derivative of numerator. Derivative of ln of x is 1 over x, and derivative of denominator 1, derivative of x is 1. Attention, you are not going to use quotient. Separately take derivative of numerator and denominator. Derivative of numerator is 1 over x. Derivative of denominator is 1. Now look at this. We have 1 over x over 1. Which if you want, you can write it as 1 over x. Because 1 over x divided by 1 is again 1 over x. What is limit of 1 over x when x approaches infinity? 0. Because in numerator we have a number. Denominator approaches infinity. Any number over something that grows to infinity is equal to 0. So the limit of 1 over x is 0. So this means that this given sequence here converges to 0. So this sequence is a convergent sequence and it converges to 0. So the limit of this given sequence is 0. Let me show you another example. We are given this sequence ln of n over ln of 2n. What is the limit of this sequence? Again, because this is in fraction form, it makes sense to use L'Hopital rule. And the other reason that we are thinking to using L'Hopital rule for finding limit of this sequence is that it is in the fraction form, and we can apply L'Hopital method for finding the limit easily. Don't forget to change the name of the variable from n to x. This is the best way to find and write your solution. So you are not going to write limit of n approaches infinity. We are going to write limit of x approaches infinity, ln of x over ln of 2x. And now we use L'Hopital rule. Derivative of numerator is 1 over x. What is derivative of ln of 2x? Based on the chain rule, derivative of ln of 2x is 1 over 2x times derivative of inside, which is 2. In numerator we have 1 over x. In denominator, if you pay attention, 2 times 1 is 2. 2 over 2x is again 1 over x. And x approaches infinity. 1 over x over 1 over x is equal to 1 because this completely cancels with this, and so the limit equals 1. This means that this given sequence here also is a convergent sequence, and this sequence converges to 1. The limit of this sequence is 1. Here, let me show you another method for finding the limit of this sequence without L'Hopital rule. Maybe the L'Hopital rule is easier, and in this video we want to find the limit of a given sequence with the L'Hopital rule if it is possible. But let me show you another method without L'Hopital rule. Note that we can write this given sequence in the form of ln of n over ln of 2 plus ln of n. Why we can do this? Let me remind you a property of ln functions. If you remember, ln of a times b is equal to ln of a plus ln of b. This is one of the properties of logarithmic functions. And also for ln we have this property. So we can write ln of 2n in the form of ln of 2 plus ln of n. So far we did nothing, just we rewrite the given sequence in this form. Now, we want to find limit of this sequence. This sequence is the original sequence, but we have written the given sequence in this form. For finding limit of this sequence, I'm going to write limit n approaches infinity of ln of n over ln of 2 plus ln of n. Now attention. When n approaches infinity, ln of infinity, because n approaches infinity, is infinity, this is also infinity, and ln of 2 is just a number. ln of 2 is almost 0.7. Anyway, it is a number. So, in this limit, we have infinity over infinity. And infinity over infinity is indeterminate form. For finding this type of limits, if you remember from before, we divide numerator and denominator by highest degree of denominator. But here, we are not working with polynomials. Here we don't have any n to the 2 or n to the 3 or n to the 5. We don't have any power of n. We have ln. Now, between these two terms, which one is the dominant term? Ln of 2 is more important over ln of n. Of course, ln of n is the bigger term, is the term which is dominant, because ln of 2 is a number, but ln of n, because n approaches infinity, is infinity. So, if we want to follow same method, which is dividing numerator and denominator by highest degree of denominator, if we follow same thing, we have to divide numerator and denominator by, we have to divide numerator and denominator by ln of n. So we divide every term in numerator and every term in denominator by ln of n. Because ln of n is the biggest term in the denominator. Now what happens? Then we have limit n approaches infinity 1 over ln of 2 over ln of n plus 1. ln of n over n, ln of n over ln of n is 1. Now, let's see what is this limit. What is limit of ln of 2, which is a number, over ln of n, which is approaches infinity? When n approaches infinity, ln of n approaches infinity. So we have a number in numerator, but in denominator of this fraction we have infinity. Any number over infinity is 0. So this limit is equal to 1 over 0 plus 1, which is 1 over 1 is 1. Same answer. This is another method for finding this limit. Now look at this example. N times e to the negative n. This is not in fraction form, but easily we can rewrite this given sequence in the form of n over e to the n. Because the power of e is negative, we can move this term to the denominator. This is one of the properties of exponential functions. We can move that term to the denominator and we make the power positive. So basically we want to find limit of x approaches infinity. Don't forget, it's wrong to write n approaches infinity. And taking derivative of n in a given sequence is integer. And you cannot take derivative of integer because integers are discrete numbers. You can take derivative when the variable is continuous. Anyway, that's another story. So first we have to write the given sequence in terms of x. Now we have a expression in terms of x. We use L'Hopital rule. Based on L'Hopital rule, derivative of the top is 1. Derivative of e to the x is e to the x. Now we have a number in numerator, but denominator is e to the infinity. Exponential function e to the x when x approaches infinity is infinity. And 1 over infinity, any number over infinity is 0. So this given sequence is convergent and converges to 0. Let me generalize this example here for you and tell you a general fact that you can keep in your head. It's really helpful for finding other similar limits. Limit of n approaches infinity of n, like here, n, not n to any power. N to the power of 2, n to the power of 3, n to the power of 1 billion, doesn't matter, the constant. N to the power of p, which p can be any number. For example, n to the power of 100 times by e to the negative n, which you know that you can move this down like I did here. This limit is always equal 0. So not only limit of this sequence is 0, if it was n to the 2, n to the 3, the limit is always 0. Basically, the fact that is behind this is that when you have exponential function in denominator and in numerator you have power of x, like x or x to the 2 or even x to the 10. Let's say here we have x to the 10. The growth of this function is faster than this function. So this function is much bigger than the numerator. When the denominator is significantly bigger, the limit is 0. Let me basically generalize this fact to this form. Limit of n approaches infinity of n to the p over, because you know that we can move this down to the denominator, over not only e to the n, over b, which b can be any number greater than 1, b to the power of n is 0. This is more general than this rule. Again, I should not forget to tell you this b should be greater than 1. Let me show you an example of application of this rule. For example, suppose they ask you what is the limit n approaches infinity of n to the 10 over, for example, 2 to the n or 3 to the n, any number greater than 1.5 to the n. So any number greater than 1, even 1.1 to the n, this limit is always 0. What about this? 0. What about this? 0. So as long as the exponential part is in denominator, the exponential is bigger than numerator and the limit is 0. Look at this example. If you remember the general fact that I told you in the previous question that we did together, if you remember that limit of n to the p over b to the p, b to the n, not b to the p, b to the n, as n approaches infinity, this is always 0. So immediately you can say that this limit is convergent and converges to 0. But we want to prove this. We know that the limit is convergent, the limit exists, the limit is 0, but we want to prove it. Because basically, if you note, this is in this form, n to the power, which is 2, over b is 3 to the n. So we know that this limit is 0 based on this rule. But let's prove this with the aim of L'Hopital rule. First, we write this in the form of x to the 2 over 3 to the x approaches infinity. We take derivative from the top, 2x. What is the derivative of 3 to the x? The derivative of 3 to the x is 3 to the x, like e to the x. The derivative of e to the x is e to the x. The derivative of 3 to the x is 3 to the x times by ln of 3. Let me remind you this general rule. Derivative of b to the x, which b is a number, is b to the x times by ln of b. But we have to take derivative again because still this is infinity over infinity. X approaches infinity, this is infinity, this is also infinity. So we have to apply basically L'Hopital rule again. By applying L'Hopital rule again, derivative of 2, numerator is just 2. For finding derivative of denominator, don't use product rule because you don't need to do that. This is a coefficient for this. This is a number. We don't have any x here. Just take derivative of 3 to the x and consider this as a coefficient for that. And after you took derivative of 3 to the x, multiply it by the ln of 3. Derivative of 3 to the x is 3 to the x ln of 3. But we had ln of 3 before. So ln of 3 times ln of 3. What is this limit? It is 0. Because we have a number over infinity. 3 to the infinity is infinity. From the beginning, we knew that this is 0. But now we have a proof. What about this sequence? Is this sequence convergent or divergent? If it is convergent, it converges to what? Yes, you are right. This is again an example from that general rule. This is convergent to 0 because this is in the form of limit of n to the p over b to the n, and the b is greater than 1. N approaches infinity, this limit is always 0. And because this is very similar to the previous example, I'm not going to show you the proof with the L'Hopital rule. It's exactly the same as previous example. Now look at this example. This is a really interesting example. What is limit of this sequence? Is this convergent or divergent? Note that we want to find limit of n approaches infinity, n times sine of 1 over n. When n approaches infinity, this is infinity. This approaches infinity. It's wrong to say this is infinity. This approaches infinity. The limit of this is infinity. What about this? This part, we have 1 over n, and now n approaches infinity. So this part approaches 0. And sine of 0 is 0. So this is 0. Infinity times 0 is indeterminate form. Don't make this mistake to say this is 0. No. 0 times infinity, because it's times by infinity. 0 times by 5, 0 times by 1 billion is 0. Yes. But 0 times infinity is indeterminate. Maybe you ask yourself, why 0 times? We knew that from before, from elementary school, 0 times anything is 0. Yes, that's right. But not 0 times infinity. For this reason, please listen. This 0 that you have written here is not really 0. The limit of this is 0. This approaches 0, not real 0. So this is close to 0. When something approaches 0 times infinity, it can be non-zero. This product can be something other than 0. Maybe the limit is 0, maybe not. So we have to figure out a way to find this limit. So we put a question mark here. Because we want to find limit of this sequence with the aim of L'Hopital rule, if it is of course possible. Let's see. The problem that here we have is that if we want to use L'Hopital rule, we need fraction, but we don't have any fraction here. We need to have numerator, we need to have denominator, then we can take derivative of numerator and denominator separately, and then we can find the limit. But here we have a product between x and times sine of 1 over x. We need to have something in the top, some expression in the bottom, a separate fraction. So we have to think about that, how we can make this in the fraction form. Let me tell you a simple fact from algebra. A times b, like a times b, always can be written as a times by reciprocal of b, something like this. So you can write any product in the form of keep one of these in the numerator and move the reciprocal of the other one to the denominator. If you pay attention, these two are equal. A times by 1 over b is ab, because 1 over b is again b. So this is right. Let me write this in a better way. A times b can be written as a times 1 over b, because 1 over b is again b. And we can write this as a times 1 a over 1 over b. So based on this, we can write this as limit of, we keep sine because sine is a complicated expression, sine of 1 over x in numerator, and we move this to the denominator and we write that x as 1 over x, or in another way we can say x to the negative 1, which makes sense because x to the negative 1, if we move it back to the top, it would be x to the 1, which is this. Now the good news is that now we have fraction. We have something in the top, something in the bottom. Now we have to find this limit. Limit of sine of 1 over x to the negative 1. And attention, 1 over x, which is in front of sine, can be written as sine of x to the negative 1. So let me write this in the form of limit of sine of x to the negative 1 over x to the negative 1. Maybe in this way finding derivative for u is easier, because we want to use L'Hopital. What is derivative of the top? Derivative of sine is cosine times by derivative of inside. What is derivative of inside? Derivative of inside is negative 1x to the negative 2. What is derivative of the denominator? Negative 1x to the negative 2. These two cancel each other, and we have just x to the cosine of x to the negative 1. So we have limit x approaches infinity cosine of 1 over x, or x to the negative 1. When x approaches infinity, this approaches 0, and cosine of 0 is 1. So this shows that this given sequence here converges to 1. Now look at this example. N to the 2 times 1 minus cosine of 1 over. If we check, you can see that this is infinity times by 0, which is indeterminate form. So we want to use L'Hopital rule for finding the limit of x approaches infinity, x2 times 1 minus cosine of 1 over x. We need to have fraction for applying L'Hopital rule, so we keep the complicated part, which is cosine, in the top, and we move x to the 2 to the bottom, and we write it as x to the negative 2. And because I want to take derivative, I made a mistake here. This should be x. I prefer to write this instead of 1 over x as x to the negative 1. Now we apply L'Hopital rule. We take derivative of the top, we take derivative of the bottom. Let's take derivative of the bottom first. Derivative of the bottom is negative 2x to the negative 3. Derivative of the 1 is 0. So in numerator we have negative. Derivative of cosine is negative sign. So this becomes positive sine x to the negative 1. Times by derivative of inside. What is derivative of inside? Derivative of x to the negative 1 is negative 1x to the negative 2. Now let's do some simplification here. If you pay attention, we can cancel this negative with this negative, and we make it positive basically. So this cancels with this. X to the negative 2 with x to the negative 3 cancels, and only we are left with just 1x to the negative 1 in the denominator. So we have limit x approaches infinity, sine of x to the negative 1 in numerator. Again, this power with this power, negative 2 with negative 2 cancel, and negative 1 from this remains. Because attention that x to the negative 3 is basically x to the negative 2 times x to the negative 1. Only one x to the negative 1 remains. So in the denominator we have 2x to the negative 1. But because again we have x into numerator and denominator, we apply L'Hopital rule again. Then we have cosine of x to the negative 1 times by derivative of inside, negative 1x to the negative 2, and derivative of the bottom is negative 2x to the negative 2. This cancels with this, negative with negative cancels. Now, what is limit of cosine of x to the negative 1 when x approaches infinity? Don't forget this is 1 over x. 1 over x when x approaches infinity is 0. Cosine of 0 is 1, and we have 2 in the denominator, so this equals 1/2. So the limit is 1/2. This sequence approaches 1/2. Now look at this example. What is limit of this sequence? Nth root of n. So we want to find limit of n approaches infinity of nth root of n, or in another word, n to the power of 1 over n. So we want to find limit of n approaches infinity, n to the power of 1 over n. This example is really important example, and I recommend you to keep the result and the answer of the limit of this sequence in your head. This is a very good example. Limit of n approaches infinity of x, n not n, x approaches infinity. We will have to change to x because we want to use L'Hopital. How we can find this limit? The problem here is that we don't have any fraction. Let me remind you a property that you can write expressions like this in another form using ln. A to the b can be written always as e to the power of b ln of a. This is a relation. For any expression which is in the form of a to the power of b can be written as e to the power of b ln of a. First of all, let me give you a reason for this relation, why this is true, if you want to know the reason. Note that we can write this in the form of e to the power of ln of a to the b. We can move this b to the power of a. This is one of the properties of log function. Now look at here. Here we take ln from this. Then we raise this to the power of a. We know that ln and exponential function e to the power exponential function are inverse. So these two cancel each other and we are left with a to the b. So this is one way to prove that this is right. Another way that you can prove that a to the b is e to the b ln of a is to take ln from both sides. If we take ln from both sides of this relation, we have this. So we take ln from left and right. If we simplify left side, we can bring this b to the front, b ln of a. Look at here. We have ln of e to the power of something. ln and e are inverse of each other. So we have b ln of a. These two are equal. This means that because this is true, this is also true. This is another reason for this relation. Anyway, keep this in relation in your head. Now, by using this relation for finding this limit, we can write this limit in the form of limit x approaches infinity e to the power of b. What is b? b is 1 over x. ln of a, which is the base, ln of x. Now, attention, x approaches infinity and only we have x here. So basically we have to find the limit over here because e is a constant. So I can rewrite this in the form of e to the power of limit x approaches infinity, limit of 1 over x ln of x. Now for finding this limit, attention, we can write this as ln of x over x. ln of x times by 1 is ln of x over x. Now finally we have what we need. We have fraction. This is in the numerator, this is in the denominator. For finding this limit, focus here. For finding this limit, we have to take derivative of numerator, derivative of denominator. What is derivative of numerator? Derivative of numerator is 1 over x. Derivative of denominator is 1 and x approaches infinity. This limit equals 0 because this is 0. And e to the 0 is 1. This means that this given sequence here converges to 1. Is a convergent sequence and it converges 1. For finding this limit, another way other than using this relation, which is a very good idea to use this relation, another way that you can find in many textbooks is that they name this something like y or u or a, whatever, and then after they consider this as a, they take ln from both sides and they get to here, they find this limit, and at the end they raise their answer to the e to the power of their answer. But I thought that this method is maybe a little better for here at least. Before I show you the next example, let me show you the general form of this sequence, which can be helpful for you for other limits of sequences. If we have a sequence in the form of nth root of not only n to any power, let's say n to the 2, n to the 3, n to the 5, n to the p, n to any power, this is also 1. And the proof would be very similar to this. You can follow same pattern, same way, same method to prove this in general. So based on this rule or this fact, consider this nth root of, for example, n to the 2. What is the limit of this sequence? 1. What about this? 1. What about if we add 5 here? Again 1. Attention, here is the nth root. As long as here we have a polynomial in terms of n, the limit of this sequence is always 1. And the proof is something like this. Now look at this example. We are given this sequence, nth root of a constant c. C is a constant greater than 0. For example, what is the limit of this sequence? Nth root of 2 or nth root of 5 or nth root of 1000. C is a constant. First, we rewrite this given sequence instead of this form in the form of c to the power of 1 over n. Now we rewrite this in terms of x. So we want to find limit x approaches infinity of c to the power of 1 over x. If you pay attention, the proof of this is really simple. We don't need to do basically anything. Because x approaches infinity, what is the limit of this part? The limit of this part is 0. So basically this equals to c to the 0, and any number greater than 0 to the power of 0 is 1. So the limit of this sequence is 1. Remember from previous question, I showed you that limit of n to the power of 1 over n approaches infinity is also 1. And in general, I told you that limit of n approaches infinity, nth root of any polynomial, not only n to the 2 plus 5n or 7n or whatever plus 7, this is also 1. This is very special case of this general rule that already we know. As long as inside the nth root we have any polynomial, not just a constant, n to the 2, n to the 3, n to the power of 1000, whatever, plus a constant like 7 here, plus 5n, all of these limits are always 1. Why here we don't need to use that a to the b equals e to the b ln of a technique? Because for finding this limit, we don't need L'Hopital. It's very straightforward. It's very clear that limit of c to the power of 1 over x is c to the 0 and it's 1. We use L'Hopital when we have a fraction here, and in that fraction numerator we have infinity, in the denominator we have infinity, but here is just 1 over infinity, and 1 over infinity is 0. So we don't need to use L'Hopital rule, and we should not basically use L'Hopital when we don't need L'Hopital. I hope by watching this video now you have learned how we can use L'Hopital rule for finding limit of sequences.